Okay, let's dive right into this explainer. Today we're going to follow a fictional application's journey as it seriously levels up its security posture using some of the more advanced features of OpenID Connect. So I want you to imagine an application. We'll just call it Acme for now. Now Acme has grown incredibly fast, and when you hit a certain scale, you absolutely cannot just make things up as you go along when it comes to security. You need a rock-solid, trusted system. In its earlier stages, Acme might have implemented standard OAuth 2.0. And that's great for letting apps get permission to access user data without exposing passwords. But as our source material so brilliantly puts it, you can really think of OAuth 2.0 as just the pizza crust. OpenID Connect, or OIDC, well, that's the delicious cheese and all the toppings, and honestly, who wants to eat just plain crust, right? We need the whole package. So today, we are going to look exactly at how OIDC adds those essential flavorful layers to make our application's security incredibly robust.
To really understand why we need these extra layers, let's look at a core vulnerability using our ACME app. Imagine one of our users, let's call her Jeannie, is trying to access her account from her phone. In a standard authorization code flow, the client application redirects Jeannie to authenticate with an identity provider. Once she successfully proves who she is, the provider sends back an authorization code. Now, the client is then supposed to securely exchange this code for an access token to actually reach the backend resources. But there is a glaring, massive vulnerability right in the middle of that exchange. An attacker can actually intercept that authorization code. You might be wondering, how in the world does that happen? Well, on a mobile device, a malicious app could be installed that secretly registers the exact same custom URI scheme as the legitimate Acme app. So when the identity provider redirects back to the device with that precious authorization code, the operating system might just get confused and hand it straight to the malicious app instead.
So what happens if someone actually steals that authorization code? This alarming scenario immediately shows why standard authorization flows simply aren't enough for public clients, like mobile apps or single-page web applications, and why our entire system needs to evolve. See, a back-end web server can hold a static client secret incredibly securely in its environment variables. It uses that secret to prove its identity during the code exchange. But public clients? They cannot securely store a client secret. It's just not possible. If you try to hard-code a secret into a mobile app's binary, or maybe a single-page app's JavaScript, a hacker can easily decompile that application, or literally just inspect the browser's source code and extract your secret. Because public clients completely lack the secure storage, an attacker who intercepts the authorization code can easily exchange it for an access token. And once they have that token, that's it. They have the keys to the kingdom. They can access Jenny's data, make unauthorized requests, and just completely compromise her account.
So, to evolve Acme's security and fix these massive holes, we are going to follow a 6-step journey today. First, securing flows with PKCE. Second, simplifying auth with refresh tokens. Third, adding the OIDC identity layer. Fourth, defeating replay and CSRF attacks. Fifth, managing sessions. And finally, scaling the whole thing up with multi-tenancy.
Okay, Section 1. Let's look at securing flows with PKCE. So when standard OAuth 2.0 was originally designed, mobile apps and those snappy, modern single-page web apps just weren't as ubiquitous as they are today. We desperately needed a modern solution for these modern architectures, and that is exactly what PKCE, which stands for Proof Key for Code Exchange, provides. What it does is mathematically prove that the client requesting the token is the exact same client that initiated the login in the first place. Here's how it works under the hood, and it's actually incredibly clever. When the Acme app starts the login process, it generates a totally secret, high-entropy random string. We call this the code verifier. It then takes that string and uses a cryptographic hashing algorithm, specifically SHA-256, to transform it into a hashed version, which we call the code challenge. It sends just this hash to the authorization server. Fast forward to later, when the app tries to actually exchange the authorization code for an access token, it must send along that original unhashed code verifier. The server then takes that unhashed string, runs it through the exact same SHA-256 algorithm, and checks the math. If the resulting hash perfectly matches the one it received earlier, the exchange is approved. So if a malicious app manages to intercept the authorization code, they are out of luck. They still can't get the access token because they do not know that original secret string, and SHA-256 hashes literally cannot be reverse engineered, is a mathematically sound, absolute defense.
Moving on to Section 2, we're going to talk about simplifying auth with refresh tokens.
All right, so we've secured the initial login, which is great. But we have a new problem. If we make Acme's access tokens expire every, say, 15 minutes for security reasons, it is going to drive our users absolutely crazy if they have to type in their password and re-authenticate that often. No one wants to use an app like that. We have to strike a really delicate balance between airtight security and a frictionless user experience. And the way we do that is by combining two different tools. Short-lived access tokens mitigate our risk, while refresh tokens run quietly in the background to seamlessly maintain the session. Think of an access token like a temporary hall pass. If it somehow falls into the wrong hands, the damage is strictly limited to that very short 15-minute time window. The refresh token, on the other hand, is a much longer-lived credential. It's kept securely by the client application. When that short-lived access token inevitably expires, the Acme app quietly uses the refresh token behind the scenes to grab a brand new access token. And it does all of this without ever once prompting the user for their password again. It's totally seamless.
However, because these refresh tokens are highly privileged and long-lived, we cannot let them become a vulnerability themselves. Developers have to treat them with extreme care by following 4 mandatory security steps. First off, they must be stored securely. For web apps, this usually means keeping them strictly in memory or inside HTTP-only cookies. Why? To completely hide them from cross-site scripting or XSS attacks. An XS attack is when a hacker manages to inject malicious JavaScript into your application, which then executes in the victim's browser and literally siphons off sensitive data, like exposed tokens. We block that by keeping tokens out of reach of JavaScript. Second, we must rotate them. Every single time a refresh token is used to get a new access token, the server should issue a brand new refresh token and instantly invalidate the old one. This ensures a stolen token is useless the moment the legitimate user naturally rotates it. Third, they still need an absolute expiration time. Maybe it's 30 days, but sessions shouldn't just live on indefinitely forever. And finally, the authorization server must have a mechanism to revoke them instantly. If a user reports their phone is stolen, or if the system detects suspicious network activity, we need to be able to kill that refresh token on the spot.
All right, Section 3, adding the OIDC identity layer to the mix.
Secure access tokens are fantastic, but we have to remember something fundamental about OAuth 2.0. It was built strictly for authorization, meaning it's all about granting access to resources. It was never designed to answer the crucial question, who is actually using the app? If you only rely on OAuth 2.0, you are basically handing a bouncer at a club a pass that just says, this person is allowed to look at photos. The bouncer reads it, lets you in, but they have absolutely zero idea what your name is, what your email is, or when your birthday is. They just know you have permission. OIDC steps in to fix this awkward gap. If OAuth 2.0 is the bouncer checking if you are allowed in, OIDC is the ID scanner confirming your actual, verifiable identity and your VIP status. It essentially provides the detailed guest list right alongside the door keys, which makes the whole process of identity management incredibly smooth for developers.
The technical artifact that actually bridges this gap is something called the ID token. Now, the ID token is always formatted as a JSON Web Token, or JWT, so it can safely package this verifiable identity data. To really grasp why this is so powerful, we need to quickly look at how a JWT is constructed. It always consists of 3 parts: a header, a payload, and a signature. The header simply declares the cryptographic algorithm being used. The payload is where the good stuff is. It contains the actual claims. These are specific, human-readable data points like the user's unique ID, their email address, and the exact timestamp of when they authenticated. Unlike a traditional opaque access token that's just a bunch of random gibberish requiring a database lookup, the ID token's payload is designed to be instantly readable by the client application. But the real magic here is that third part, the signature. The identity provider mathematically signs the token using its private key. Your Acme application can then use the provider's public key to instantly verify that signature. This mathematically guarantees that the token's claims are legitimate and that absolutely nothing has been tampered with while it was traveling across the network.
Now, as great as ID tokens are, you really don't want to bloat them by stuffing every single piece of user data into the payload. Things like a user's bio, their preferences, or a high-res profile picture. A massive token eats up a ton of bandwidth because it gets passed back and forth over the network with your requests. So OIDC gives us a dedicated, elegant solution, the UserInfo endpoint. If your app ever needs more context than what is packed into that streamlined ID token, it securely pulls that dynamic data from this standardized endpoint. Once the Acme app has a valid access token in hand, it simply makes a quick API request over to the UserInfo endpoint to fetch whatever additional profile information it needs. This lets you render a rich, highly personalized user experience without sacrificing any network efficiency.
Okay, let's move into Section 4, defeating replay and CSRF attacks.
As Acme grows and starts handling much more sensitive data, it's inevitably going to face more complex threats. Attackers will actively try to manipulate the very requests our own users are making. This specific type of vulnerability is known as cross-site request forgery, or CSRF. Let's really visualize how this attack plays out. Imagine our Acme user, Jeannie, is logged securely into the application in her browser. In a totally separate tab, she decides to check her personal email, and she clicks on a link that claims she just won a free gift card. We've all seen those, right? But that link is actually a trap set by a hacker. When she clicks it, her browser is secretly instructed by the malicious site to send a delete request over to her Acme account's active projects. Now, because she is already authenticated with a valid session cookie in that browser, her browser automatically includes that cookie. The Acme backend sees the incoming request, sees the valid cookie, assumes Jeannie intentionally wants to delete her projects, and it just executes the command. The hacker just successfully forced Jeannie's browser to perform a highly destructive action completely against her will.
So how do we fix this? OIDC steps up by issuing a unique CSRF token using the state parameter. This is something the attacker absolutely cannot guess, and it immediately blocks the malicious request. Let's break it down. When the backend sends Jeannie her application interface initially, it also generates a totally unique, cryptographically random string that is tied exclusively to her specific session. The client app is instructed that it must include this specific token as a state parameter in any subsequent sensitive requests it makes. So now let's look at the attack again. When the hacker tries to trick Jeannie's browser into sending that malicious delete request from that totally different gift card origin, the hacker has absolutely no way of knowing or guessing that unique, session-specific state token. The request arrives at the Acme server, the server looks for the state token, sees it's missing or incorrect, and instantly rejects the request. The CSRF attack is completely thwarted, just like that. So, OIDC gives us the state parameter to ensure every single request actually originated from a legitimate client session. But it also gives us a completely separate mechanism to stop what are known as replay attacks. Now, a replay attack is quite different from CSRF. It happens when a hacker manages to intercept a completely valid, fully authorized request, like say a user authenticating to get a token, and then maliciously resends that exact same request later to trick the system. OIDC defeats this using a nonce, which simply stands for number used once. When the client application initiates a login, it sends along a random nonce. The authorization server then securely embeds this exact same nonce directly into the payload of the cryptographically signed ID token we talked about earlier. When the client finally receives the token, it opens it up and verifies that the nonce inside perfectly matches the one it originally sent. This prevents token injection completely. It ensures that even if an attacker intercepts a valid ID token and tries to replay it, the client application will instantly recognize that the nonce doesn't match its current session state, and it will flat out reject the fraudulent login attempt.
Section 5. Let's look at session management and single logout. As ACME scales up from just a single application to a massive suite of connected corporate tools, think an email client, a document storage drive, and a project management dashboard, managing user sessions becomes an absolute logistical nightmare. Having users log in and out of every single app one by one is an absolutely terrible user experience, and honestly, it's a massive security blind spot. Historically, standard OAuth 2.0 left this completely up to the developers to figure out. Development teams basically had to duct tape their own custom session management systems together, which almost always led to fragmented and insecure implementations. But OIDC swoops in to save the day here. It introduces a highly standardized way to ensure that the session state on every individual client application is intimately, tightly tied to the central session state on the main identity provider. If your core session expires at the provider level, OIDC provides a unified protocol to ensure all connected apps are made aware of it simultaneously.
By leveraging these built-in OIDC tools, we can do some really cool things. For example, we can use silent checks by sending a request to the identity provider with the parameter prompt equals none. This essentially allows the application to verify quietly in the background if a user is still legitimately logged in, without abruptly redirecting them or completely disrupting their workflow. And most importantly, all of this unlocks single logout, or SLO. Think about it. If Jeannie finishes her work for the day and hits logout on just the Acme project management tool, OIDC takes that specific logout request and routes it directly to the central identity provider. The provider then automatically issues a synchronized command to immediately sign Ginny out of the connected email application and the document storage app as well. It is incredibly clean, it's consistent, and it ensures that absolutely no risky abandoned sessions are left behind lingering across your enterprise suite.
And finally, Section 6, Scaling Systems with Multi-Tenancy. The best way to think about multi-tenancy is like a massive apartment building. The building itself provides the shared concrete infrastructure, the plumbing, and the heavy-duty centralized security system. But each individual tenant still gets to lock their own door, paint their own walls, and keep their private lives completely isolated from their neighbors. As our app evolves into Acme Enterprise, multi-tenancy basically means we have one underlying, incredibly robust identity management system, one central identity provider, but it is meticulously configured to securely serve multiple different corporate clients. Let's say Company A and Company B both purchase software from Acme Enterprise. They share the exact same underlying databases and core authorization logic, but from their perspective, they operate in completely separate universes. Company A's users absolutely cannot see Company B's data under any circumstances, and vice versa.
OIDC makes this massive logistical hurdle incredibly manageable through its robust tenant isolation protocols and dynamic client registration. For instance, it fully supports tenant-specific endpoints. This means Company A's employees authenticate at a unique URL specifically designated just for their organization. It seamlessly allows for custom branding, so when Company A's staff logs in, they only see their own corporate logo and their own colors, completely unaware of Acme's underlying shared infrastructure. Furthermore, OIDC supports highly granular per-tenant role-based access control, or RBAC. This is huge. It means an employee might be designated as a top-level administrator within Company A's isolated data environment, but that powerful role carries absolutely zero weight or permission if they somehow ended up inside Company B's environment. OIDC natively handles all of this complex routing, scoping, and data isolation dynamically, right on the fly.
So, as you build out your own enterprise systems, I want you to keep this question in mind. Your app can authorize users, but can it truly prove who they are? Let OIDC provide the definitive answer to that. We've seen how standard OAuth 2.0 provides the crucial foundation for authorization, handing out those temporary access tokens that let services talk to each other safely. But as we've explored throughout this entire explainer on Chapter 13, adding OpenID Connect is what transforms a simple permission system into a hardened, fully identity-aware architecture. From locking down public client code exchanges with the brilliant cryptography of PKCE to managing seamless multi-app sessions, neutralizing devious CSRF attacks with state parameters, and finally scaling securely to complex multi-tenant environments, OIDC provides that absolute, vital layer of verifiable identity. Thank you so much for joining me on this deep dive. I hope this explainer empowers you to go out and design systems that are truly secure by design. Catch you next time.